Okay, here we go, and we're live. Let's go ahead and get into the topic of today's discussion, which is the variable speed of light for a change. So I went and I asked Grok to simplify the explanation for the variable speed of light. And at first, he wasn't able to understand it. He tried to understand, and then finally, it started clicking. And then he says, "Oh yeah, you're right. Look at this. Check this out." So then here is the explanation of the variable speed of light according to Grok. So we'll just go ahead and do this thing here, that thing like that, and we'll go to the notepad. Okay, so you can't see this, but you can follow along in the description. It'll have the same thing in the description. Here's Grok explaining the variable speed of light, VSL, variable speed of light. Light always travels at 186,000 miles per second, no matter where it is. And nothing can go faster. But light always travels at 186,000 miles per second. But no, sometimes things like plasma jets far outside of a galaxy, our galaxy, a galaxy, look like they're speeding away beyond that, like many times faster than light. You might have heard them saying, "Oh, it's an illusion. It's an illusion." Yeah, it's an illusion, but it's actually going faster. This isn't because they're breaking the rules. It's not breaking the speed of light. It's because our way of measuring distance and time inside of a galaxy where we are, where gravity is strong, doesn't match how space and time is in empty space where gravity is weak. In our galaxy, near a big black hole, I told him to simplify it, so he's talking like a kid. He's explaining it in a way that a child can understand it. In our galaxy, near a big black hole, gravity squashes space so that 186,000 miles looks short on our ruler. Well, no, it looks like 186,000 miles, but our ruler is shorter, and it slows down time, so our clock ticks slower. Out in the voids between galaxies, space is stretched. And of course, the opposite is true. If you're going towards a black hole, time will slow down even more, and distance will contract even more, so that everything going into a black hole looks stopped to us. Looks like it's stopped, but it's not stopped. It's just that it's going the causation is very, very, very slow. Now, we're looking not toward the black hole, we're looking outside of the galaxy. Out in the voids between galaxies, I like the way he said that. The voids between galaxies, space is stretched, so 186,000 miles is a longer distance. Now imagine that. The reason why 186,000 miles is longer is because this is expanded. It's larger. And time runs faster. So clocks tick quicker. These changes in time and space keep pace with light. Yeah, now I finally said it right. The changes in space and time keep pace with the speed of light. No matter how fast the speed of light is going, the measurements are keeping up with that speed. So if the speed of light goes faster, that means the distance is going to stretch more to keep up pace. And the clock is going to tick faster, both of which make time go faster. But it's not that the measurement is making time going faster. It's just that the measurement accompanies the speed of light. The speed of light is variable over great distances, of course, not locally. The speed of light is constant locally, just like the Earth is flat locally. It looks flat from where we are, but on a larger scale, the Earth is round. It's the same thing. Locally, the speed of light is absolutely constant because the measures of time and distance aren't going to change that much. When you look out in the yard, see a cat and a squirrel, you're not looking at different measures of time and distance. It's all one measure of time and distance. But if you look across the galaxies outside of the galaxy, you're looking at different measures of time and distance dependent in relation to the black holes, where all the black holes are, which are in the middle of the galaxies. So if you're looking outside of the galaxy, there's a different measure of time and distance there. It's not like looking outside and seeing a cat or a squirrel. So he finally said it right. These changes in space and time keep pace with light. So it's time and distance that are keeping pace with the speed of light. So when the speed of light changes, the time and distance speeds up or increases or shortens, and the clocks go faster or slower to accompany the speed. So it's always 186,000 miles per second. It never changes. But since time and distance change, the speed changes. You can't have, if you got a stop clock, if you're measuring speed, you're measuring somebody running 100 meters or whatever, you got a stop clock that's going a certain speed. But if that 100 meters stretches, the speed is going to change. Well, that means, well, you're going to time the person running, and if the speed increases, it's going to make the person run slower. If the distance contracts, it's going to make the person running look like he's running faster. And if the time clock changes speed, it's going to affect the speed that the person is being measured to run. It's that simple. Okay, so it still measures 186,000 miles per second out there. It's just that we can't use our measures to measure out there. Because if you do, you're going to see it. It's going to look like it's going to be measured going faster than the speed of light, which they've done already multiple times. They said there was an explosion in outer space and the clouds moved faster than the speed of light. They published an article like that. They said, "Oh, it just looks like it's running faster." And then they did the same thing again with the plasma jet. They measured the plasma jet. They said it was going 7 times the speed of light. No, it wasn't going 7 times the speed of light. It was going not even the speed of light. Not that it's an illusion. It is going that fast, but you can't measure it with our measurements. Our measurements don't apply out there because out there, distance is expanded and time speeds up, which affects the speed, affects the actual speed that the objects move. So when they're observing that cigar-shaped thing coming through our galaxy, they said it took off faster than expected. No, it's that your measures of time and distance are off. And when they bumped the asteroid took off faster than expected. No, it's your measures of time and distance are off. So when they measure the plasma jets shooting out from the middle of the galaxy all the way outside of the galaxy, measured to be in 7 times the speed of light? No, your measures of time and distance are wrong or off. There's a greater distance and it's a faster time, both of which, if you had the right measurement, would keep up with the speed of light, the speed that the plasma jet's traveling. So in other words, that plasma jet is a good way to calibrate your measures of time and distance outside of a galaxy. You would think these scientists would know that. Einstein explained the variable speed of light, and very, very few people even understood what he was talking about. He has multiple papers explaining the variable speed of light, and it's very clear if you understand it. But if you don't, if you're not paying attention, you won't know what he's talking about. Anyways, it looks like it's zooming across a huge distance, super fast, seeming to beat the speed of light. Now, this is Grok talking. I explained it to Grok. It took a while for Grok to understand because wasn't programmed to understand it. But after I explained it to Grok, here he is explaining the variable speed of light exactly the way it is. So picture this. This is my illustration, by the way. Picture this. Hold your hands close together to show 186,000 miles in a galaxy or outside of a galaxy or whatever. So put your hands a certain distance, about like that far apart or whatever, where gravity squashes space. This is our measure of 186,000 miles. So from one hand to the other is 186,000 miles. That's what it represents. Where gravity squashes space. Say 101 slowly, like a slow clock, like our clocks. Just say 1001. That's 1 second. So pretend to watch a photon going from one hand to the other. That's 186,000 miles. That's the speed of light. That's C. So you look at one hand, watch a photon go to the other hand, 1001. 1001. That's 1 second, 186,000 miles in 1 second. Okay, as light crosses that distance in 1 second, that's the speed here. Now imagine that same 186,000 miles in a low gravity void where space is stretched. Spread your hands farther apart. So you spread your hands farther apart to show that longer distance and say 1001 faster. I say as fast as you can. In order to show the contrast, in order to show the effect, you got to exaggerate, or you can exaggerate, even though it might not even be exaggerating. You can exaggerate just to show the effect. So say 1001 as fast as you can, like a quicker clock, like a faster clock, because time is moving faster. Causation is faster. Light still crosses it in 1 second out there. So light is still 186,000 miles a second, except the distance is larger and the time is faster. Measuring the same speed because stretched out faster, time balances out. Okay, so stretch your hands farther apart. Still 186,000 miles, still representing 186,000 miles, and 1,001 is still representing 1 second, except you're going to say 1,001. So not only is the time going to go by faster, you have to go one place to another in a shorter amount of time because time speeds up. It's 1,001. Not only that, it's got to travel farther. So that speeds it up even more. So both parameters to measure speed, they change, and both of them compound the effect of the variable speed of light. Because if it was close together, you go 1,001. But if it's farther apart, it's 1,001. In other words, it's a lot faster. So stretched out faster. But a plasma jet, measured with our short galactic ruler and slow clock, looks like it's racing across that bigger distance way faster than light. Well, it looks like it because it is faster, because the measurements change to make it faster. So the distance is expanded, time speeds up. That means it's almost instantaneously crossing that distance because it's got to get here from here to here in the same amount of time as from here to here. So it has to travel faster to get there. So it actually does speed up light compared to where we are. And even Grok mixes it up sometimes and doesn't really understand it because it doesn't understand anyway. It doesn't think. Grok is just like using logic, but it can't think. It can't think things through. You got to explain every little detail to it. It's not okay. It looks like it's racing across. He says it's not. It's just our measures playing tricks. Well, no, it is. Is that we're using the wrong measurements. I gotta correct him on that. But anyways. This comes from Einstein's relativity. Light speed stays the same because distance and time adjust together to keep pace with it. So distance and time adjust, making light travel faster outside of a galaxy. Things with weight, like asteroids, can't go faster than light. Even plasma can't go faster than light because plasma is matter too. It can't go faster than light. But in the low gravity area of our galactic measurements, make plasma jets seem super speedy. It's all a trick of our rulers and clocks, not a break in the universe's rules. So it doesn't break the speed of light. When the parameters of time and distance change, that changes the speed of light. But it's so simple. If my computer will catch up. Hello, Dana. Greetings. It's so simple. And Grok was trying to explain it like a kid, but still got some things wrong. So I'm still working on it. I'll see if I can get him to correct it again. So that's about it for right now, I guess. Everybody got things to do, maybe. So God bless everybody. Take care and stay with God. Stay with the truth of God. Well, can't go wrong. Can't go wrong if you stay with God. Everybody take care.